I'll start this video by stating that specific gravity, the one that I discussed before in the previous video, is dimensionless or no units. Unlike the variables that I'm going to discuss, which have units, and the units could be, as we discussed before, SI units, CGS unit, or American system. It's not gold or silver. Starting with a density equal to 1000 kilogram per meter cube if we are talking about water. Now, why am I stating water only? Because most of the chemicals that we will be dealing with when we are asked to find their density, liquid or solid, then we will find the density with respect or relative to the density of water in order to use it then with the specific gravity to find the density of the chemical. In CGS system, gram per centimeter cube, here SI, here CGS, and in American system, the one that is always far away from these two, 62.43 pound mass per feet cube. Once again, this is not the element for gold, it's just American unit shortcut. All of these densities of water are calculated at T equal to 4 degree. If you calculate this density at 4 degree, and if you calculate density of water at 100 degree, the temperature at which the water boils, you will find that the density of water is equal to maybe 997 kilogram per meter cube. When we compare it with the SI unit, from 1000 to 997, and in case of CGS system, it will be 0.997, so nothing much. Using the water density, which should be memorized in all of the units, SI, CGS, and American unit, and the specific gravity that may be given to you in the question, or you may have to find it in a table, depending on the engineering book that you are reading from. Use it with the density of the water to find the density of the chemical you are looking for. In my case, I'm using elementary principles of chemical processes, and if you are using the same book that I use, then if you go to table B1, you will find most of the solids and liquids. If you remember, specific gravity is equal to density of a chemical divided by the density of the water. And as we said, it will be at 4 degree. This water will be 4 degree. And this is actually why we are saying specific gravity is dimensionless, because density over density is units cancelling each other, right? So if you use the specific gravity that you find from the table or the given from the question, and then you multiply it by density of water, just that easy, you will find the density of the chemical. A quite nice rule I can say about densities: if you are asked to find the specific gravity in this unit, gram per centimeter cube, then the density of the chemical is equal to the specific gravity that you found from the table or the given one. Let me illustrate the idea. If I have a specific gravity of a certain chemical to be 0.5, and then it asked me to find the density of the chemical in gram per centimeter cube, then rest assured, and don't even think about it, the density of the chemical will actually equal to the specific gravity given in the question or you found from the table, which is equal to 0.5, and then you just put the units, gram per centimeter cube. If you are not like me, just memorize everything and you want to understand, then it's because, as I said before, you will multiply specific gravity with the density of water. But the density of water here in gram in CGS unit, it will be 1. So it will be only 1 times specific gravity, which is actually equal to specific gravity. This is the case when you consider the water as your relative point or reference density, and if it asks you to find the density of the chemical in gram per centimeter cube only. For the SI unit, I can say the same thing, but a little bit different. Suppose you have this 0.5 and it asks you to find the density in kilogram per meter cube. All you have to do is just multiply this one by 1000. Why? Because we are saying here specific gravity multiplied by the density of the water, and if it asks you to find it in kilogram per meter cube, then you will use this one to find the density of the chemical, which will be 1000 times the specific gravity given or found from the table, 500 kilogram per meter cube. So maybe you can find your way with an SI unit. Maybe or definitely you can find your way with CGS, but please don't joke with the American system, because as you can see the number is different and it has a decimal. It's not a simple number like 1000 or 1 gram. So in that case, use this rule. Specific gravity times the density of water equal to density of the chemical. And if I want to make your life harder, I could ask you to find the specific volume, a new word that makes someone terrified. But it's actually just the reciprocal. Take 1 over density, or 1 over, in this case, 500. It will be meter cube divided by kilogram. This is specific volume if you divide volume by mass, because remember, I also said in the previous video that whenever we say specific and then a word after this specific, that like volume or like enthalpy or like whatever, then you either divide by mass. Here in this case you divide by mass, because this 1 over rho is actually equal to V over M. You are dividing by mass, or you either divide by moles, but I will come to the story of moles later on. For now you can say specific volume equal to 1 over rho, which will be in this case 1 over 500, which is V over M, which is 0.02 meter cube per kilogram. Who is the correct one? Is it me, the human calculator, or the actual calculator? Okay, 0.002. So the human calculator is not correct. Makes sense? One more additional rule I can add is the relation between the density, volume, and temperature. Let's leave pressure now and focus on these three. Whenever you increase the temperature, even though I said before slight change will happen, but there is a change, so you would expect the volume to increase, because the lovely chemistry formula V1 over T1 equal to V2 over T2, and according to this relation, Charles' law, mass over density, then density should decrease. If you have larger temperature, then you will have larger space, and it would just mean that you have a less dense material. But this is not where the difficulty of the 10th drug is, because this is just the starter of the many relationship that will come now. If you know specific gravity, then you multiply it by density of water, then you find the density of the chemical. And if you have the mass of the chemical, then you would say rho equal to M over V, and from here you can find volume equal to something. And the difficulty is not only these relationships starting from specific gravity to volume, but also the conversion between them. When we want to find conversion factor for SI unit, CGS unit, or the horror American system, then we need to make sure that what we are doing is correct. I covered already dimensional analysis, but I will do this example just as a review and to illustrate this new idea. Now I will state the name of the chemical, and it is really dense. It is so dense. It is mercury. Most of the specific gravities that you will see for the liquids and the solids do not even exceed number 5, but this is 13.54, 2 times larger than 5, or maybe higher. By the way, I got this from table B1 in elementary processes of chemical, elementary principles of chemical processes. And if you know the specific gravity of the mercury, then it is enough to calculate the density of the mercury. It is just what specific gravity of the mercury, I will call M, multiplied by the density of the water. If we are considering the hardest case, American system, 13.54 multiplied by 62.4. Okay, so it will be 845.3 pound mass per feet cube. And now if I said find the volume that is occupied by 215 kilogram, you see it's also heavy. So it's not just dense, it's also heavy. It makes sense if you have larger density, larger specific gravity, and therefore it will be larger in mass. But that's not the subject here. The subject here is to find the volume. So if you have 215 kilogram, this is mass. And if you have the density of the mercury, then it makes sense that you can find also the volume of the mercury. you would expect the volume to be so small. So the mass here is 215 and the density here is 845.3. But I'm forgetting something very important here. This is 215 kilogram. So we need to convert it. 215 kilogram conversion factor. This is the difficulty of the 10th drug. It's not about using the rules that we have discussed earlier. It's about not forgetting the conversion factor also. Here we know that 1 kilogram is equal to 2.2 pound mass. It will be 473 pound mass. Substitute here this number, pound mass, divided by the density, and just do a quick dimensional analysis. It will be 473 pound mass divided by 845.3 pound mass, and here per feet cube it will rise up here. It will be feet cube in the numerator. So indeed we ended up having volume. Just knowing dimensional analysis also makes you relieved. If you see volume, then you are on the right track. So you see it is considerably small. The answer is 0.5595 or 96 feet cube. This is the volume that is occupied by this number of mass, 215 kilogram or 473 pound mass, and it is so dense. Why it is so dense? Because you have a small space. So you'd expect this larger amount to be compacted or forced together, making the density of it very high. And now many exceptional individuals will ask me, where can we use the concept of density and sensitivity with temperature? And I say that we can use it here also. Suppose you found this density of this mercury, and then you increase the temperature. So maybe here it was calculated at T equal to 30, and then because you were bored and then you decided to do something fun, you increase the temperature to 210 degrees Celsius without being melted. If you really appreciate the concept of density temperature, then you wouldn't apply all of these rules starting from specific gravity of the mercury all the way to the volume. You would just understand that increasing the temperature will not have an effect of the mass, and the density is slightly changing with temperature, which means if the density and if the mass is or are constant, it means that the volume is also constant. It means that density equal to m over v all will not change. This is the case when you have liquid. So you don't need to repeat the calculations here. What you found, I'm not saying exactly, but I'm saying is close enough to what you will find if you do the calculations again at T equal to 210. So it's about understanding. In CHE drug, do not expect something to be memorized. Most of the things that I will teach, or that I will teach myself also, I will say and I will repeat the word, understand, appreciate. The reason is, what if you will hear these words always from me? But also, I've said a certain word many times in the previous video without even introducing the real meaning of it. Production rate, mass flow rate, volumetric flow rate, a flow rate, a rate. I really did say it a lot, but only because it's very important, and because in industrial processes we have always chemicals moving, either entering from a process unit to a process unit, like this case, number 1, or number 2, either leaving as a product, maybe stored in the same facility or an industry, or number 3, maybe leaving to another company or another facility. In all cases, we would need to know the value, and the way we measure the flow rate is by common 2 methods. One is flow meter, and the other is velocity measuring devices like pitot tube. The first method, as we all know, flow meter, so it means it is the measuring device that measures the flow rate of a certain chemical, or we call it fluid, and the fluid is either a gas or a liquid. One type of a flow meter is rotameter, and there is another one which is orifice meter. Both work differently, but they measure the flow rate. Rotameter has a shape like this: a vertical tube, and then it has a certain flow rate flowing and leaving, and there is some measurements reading here. And there is the important thing, which is a float. We call it a float. This float will maybe be higher or be lower than its place, and depending on its position, you will know that the flow rate is either high or low. If the float is maybe here, then it means that the flow rate that comes inside is very high, that it pushes this float upward. And if the float is low, then you would know that the flow rate is not that high. And from this you will record the flow rate. As we defined earlier, flow rate has a word rate, and rate means with respect to time. A very important thing to mention about the rotameter is the fact that we need to calibrate it. What do we mean by calibrated rotameter? It means that this guarantees and verifies that this scale or this rotameter and the readings inside this rotameter and even the float is ready to be used. And this means that wherever this float is located, either here, this reading, or this reading, then you will take this reading and you will trust it. You will trust it and you will say that the flow rate is something something. The other measuring device that also measures the flow rate is the orifice meter, and it is actually a hole inside a pipe. So if you have a pipe, not a great drawing, but it is enough, and you have a flow rate coming inside this pipe, leaving from this pipe, an orifice meter is installed inside it. So we would have some holes here in order to make some amount of this fluid transferred here. And because we created this hole, which should be very small, not like this, should be narrow enough to create something called pressure drop, a really important term that we will use a lot when we come to fluid mechanics, which means there is a pressure difference. The pressure here is not the same as this pressure here, and this will create a pressure difference, or what we call pressure drop. And from this pressure drop, we can use an equation called orifice meter equation. I'm not gonna bother you with the equation, but know that we will use this equation in order to find the flow rate that we want in the first place. You want to measure this flow rate in order to assure that what you are producing and the amount you are producing is within the required term by the market or whatever. So you use a measuring devices, and with these measuring devices you find the flow rate. But this one use calibrated rotameter, and the float reading is the reading of the value of the flow rate, whereas in the orifice meter it uses a pressure drop that, if you relate it with orifice meter equation, you can find the flow rate that you want. Other method include pit tube, and pit tube has a similar idea as the orifice meter, but the equation that we will use is different. An equation which is very, very famous, known as Bernoulli equation. Bernoulli equation means finding the velocity, and then if you find the velocity, you can find the volumetric flow rate, which is a type of a flow rate, and which is the thing that we want in the first place. You have a pipe, again with this bad drawing. Instead of creating a hole, a U-hole, you will create something that has this shape, and this shape is open to the flow, or the tip of it is open, and the opening is inside the original pipe. You have this fluid coming here, and this will create a pressure difference, and from pressure difference you can use Bernoulli equation, not orifice meter equation, in order to find the pressure difference in this point and maybe this point. And from pressure difference and the velocity, you can find the flow rate. Someone now might say, including myself, I've said this before to myself, If you have the same idea here in orifice meter and pitot tube, why can't we use Bernoulli equation here also? And the reason is because pitot tube satisfies the condition of Bernoulli equation. The conditions involve incompressible fluid, uniform flow, laminar flow, no heat transfer. And if you use Bernoulli equation in this orifice meter, which could include one of the conditions at least, then you will be in trouble. You may not do the thing that you are asked to do from the market or from your boss because of a mistake here, or a mistake in the equation that you used. So engineering is not about memorizing at all. It's about understanding, knowing when to use a certain thing in a certain place or in a certain process. Bernoulli equation with pitot tubes, orifice meter equation with orifice meter. It also fits. I've said measuring flow rate so far, but I didn't specify which flow rate. Whenever you want to measure the flow rate, you either measure volumetric flow rate or mass flow rate. They are the easiest ones. They are the easiest flow rates to be found, especially volume flow rate. In case of rotameter, just read from the float, and with a stopwatch you can find the flow rate of the volume easily. With mass, you may do a little bit of hard work, but it's not that hard compared to other flow rates. So you will either face volumetric flow rate or mass flow rate. Especially in laboratories, the most one that you will calculate is the volumetric flow rate. But at least now you won't be surprised if your instructor, for example, said, okay, measure the flow rate using mass. And by the way, as I illustrated from the previous video, mass flow rate divided by volumetric flow rate is equal to density. So they are related by a density. And the density works as a conversion factor, and the density is easily found using what I illustrated earlier as well, specific gravity multiplied by specific or density of water. Things are really related. Even if you don't appreciate it now, just understand whatever you are facing in engineering. You will never know when to use it again. One thing I might add in measuring the flow rates is the fact that we need to wait a little bit in order to stabilize the flow, or another word you will hear, steady flow, or as we will hear later on, steady state. All means the same. And it will not be steady, or it will not be flowing at a constant rate in the beginning. So you will wait a little bit until it is stabilized, and then things will be easier just by the devices I mentioned earlier, rotameter, pitot tubes, or orifice meter. But I believe discussing these three common measuring devices are enough. The last type I want to conclude with is the temperature, and it is defined as the average kinetic energy of the molecules that are moving in a container, for example. If you have a container and you have many molecules inside it, each one of them will possess a kinetic energy, 1 over 2 mv squared. M is the mass, v is the velocity. If you sum all of these kinetic energies and take the average, it will be the temperature. And now one might wonder and say, if you say that temperature is an average of the kinetic energy, then why it is measured in degrees Celsius, for example? And the reason is temperature is a property of a system, and the energy is the ability of a certain system to do work or transfer heat. Actually, the average kinetic energy and the temperature are related. If you go back to the chemistry books and see the pages that we always ignore, kinetic molecular theory, or theory of kinetic energy, or theory of ideal gas, in these pages that we hate or we ignore, you will see that temperature and kinetic energy are related to each other. Average kinetic energy are related to each other by this formula, 3 over 2, their some constant multiplied by the temperature here. This constant is called Boltzmann constant. This is not the subject, but one of the questions that makes me wonder always why we are saying average kinetic energy, but it is degrees Celsius. This is just for gas. There is also a relationship for the solid and for the liquid. There is no fixed relationship between them, but we do know that for all the three cases, gas, solid, liquid, as you increase the average kinetic energy, temperature will also increase. This is just an introductory to temperature and what it means, but the real thing about temperature will inshallah be discussed in the next video. That's it.